Now we're going to go ahead and look at confidence intervals with an unknown population standard deviation. But before we do that, a little bit of Garfield. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And he says, this guy's never wrong. Yeah, that's because he's pretty much used a 100% confidence interval, which we won't be doing because that's not very helpful. So, first of all, if I draw a sample from a population that has a normal distribution with a mean mu and standard deviation of sigma, then x bar will have the normal distribution where you have x bar and s for n sample size. Now, as n gets bigger, the spread or variance decreases because the better the sample size, the tighter our distribution. Now, most of the time we don't know the standard deviation of the population, but we can calculate S, which is known as the standard error of the sample. Now, problems were noticed when n was not large. So what does this go back to? Believe it or not, in a brewery. Some of you have probably heard of Guinness beer, good Irish beer if I recall. And he would use small samples to test the stout, which is a very heavy, filling drink. And he didn't want to drink a whole bunch. And I'm sure if the stout was ever bad, he really didn't want to drink it. And he wanted an alpha 0.05. In other words, he expected to reject 5% of the good batch. He's like, I can live with 5% of good beer being rejected. But he found out he was actually rejecting 15% of good batches, and that's too much. So he created a new model based on his analysis called the student's T distribution. Now, these students' T distributions are unimodal, symmetric, and bell-shaped. So right here, the red curve is the student's T curve when we have a lot of degrees of freedom, like 40 here. The standard normal curve, which we've been using, is a blue one. So what happens is our degrees of freedom go down. So as I adjust the degrees of freedom here, you can see that this is starting to come down a little, and then these tails are starting to get fatter. So they have fatter tails, which means we're going to have a larger margin of error compared to a normal distribution, and something I'm going to teach you about later called larger p-values. Now, t-values or t-scores are like z-scores or z-critical values, but have a different model for every degree of freedom. You can see this is degree of freedom 1, and when I had it all the way to 40, it looked a lot like a normal distribution. So as the degrees of freedom increases, this distribution looks like the normal. So how to get a t-value from probability on the TI-84. So remember how we did inverse norm? To get a z critical value, we're going to do inverse t. You start that by pressing second distribution, there it is, second distribution, and go to that inverse t, which is item 4. All right. Then you're going to put in your probability, and then you're going to add one extra thing. Remember, this is the area to the left. You're going to have your degrees of freedom. So here's a t-score for 0.99 to the left and 6 degrees of freedom. We can do it again with a higher number of degrees of freedom. So we're still doing 0.99, but now we have 20 degrees of freedom. And it's churning. That's what that little line is that you see moving. And you can see the higher our degrees of freedom, the closer it is to a normal z critical value. So this returns a t-value, which the probability to the left of that value is the entered value and the specified degrees of freedom. So it's the area to the left, just like inverse norm. So use students' t distribution to find the critical value for t at an 80% confidence level when the sample size is 32. So I'm going to pretty much use exactly the same thing I was using with inverse norm, except instead of inverse norm, I'm doing inverse t. 1 minus 0.8 over 2, comma 31. By the way, your degrees of freedom is always your sample size minus 1. So we do inverse t of 0.10, 31, and I get negative 1.31. By the way, if you do these with these lower values, you will get a negative. But usually when we're using them, we don't worry about it. We say, well, we'll use the positive value. So if I'm doing 80% with the sample size 64, the only thing that changes is my degrees of freedom, And you can see it's 1.30. It really should be negative 1.30. Um, and basically, that's really similar to the other value, just a teensy bit tighter because of our larger sample size. So which t-value is larger? The one with the fewer degrees of freedom. So the less freedom we have, the wider we have to make our interval. Although that does sound kind of odd, but it's true. It's totally true. All right, so we're going to go ahead and construct and interpret a 99% interval. So I have a sample of 50 math scores. They had an average of 570 and a standard error from the sample that we could have calculated using one of our stats. And we're going to go ahead and make that 99% confidence interval. So here's my stats from my sample. I can find my new standard error for a mean by dividing that 85 by the square root of my sample size, which is 12.02. I can find my critical value. There are 49 degrees of freedom because it's the sample size minus 1. So it's inverse t. I want 99% confident. So 1 minus 0.99 over 2 with 49. So if I go ahead and construct my confidence interval, it's going to be my mean plus or minus 2.68, which is my t-value here. And it doesn't matter if I use positive or negative because I'm supposed to use both here anyways. And then here is my standard error. And if I go ahead and find those two numbers, there's my confidence interval. If I need to interpret it, I can say we are 99% confident that the true SAT math score at Cedar Ridge is between 537.78 and 602.22 based on this sample of 50 scores. Now, here's the good news. Your calculator also will automatically do this for you. So you're going to press Stat and Test. So we've been going there a lot. You're going to scroll to this puppy, 8t interval. For the input, if you have the stats where you have x bar and s of x and n like we do here, go ahead and press enter there. And for x bar, enter your mean. For s of x, enter your standard error for the sample. And for n, enter the sample size. For the confidence level, enter the desired confidence level. Remember, it should be in decimal form. And then when you press calculate here, you'll find that there's your interval. So that actually matches what we got earlier. Now, if you have a list of data, which is really common, you're going to enter your data in a list by pressing Stat and Edit, just like we did before. Put your data in list 1. Press Stat and scroll to Test, like we just did. Select T interval, same steps. This time you're going to select Data, and then you're going to put list 1 in. Make sure your frequency is 1, unless you have a second list of frequencies in list 2, in which case you should put it there, although we don't do too much with frequencies. And put your confidence level in decimal form and hit calculate. Oops. So if you look at it, here's the output, which is actually going to kind of go to what we were looking at in our next example. So here I have a coffee machine dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. So here are the amounts in a random sample of 20 cups. So let's say I already entered this data in a calculator, all right? And so the data is all entered in the list, and I just want to go ahead and calculate the interval. So I'm going to go Stat, go to Test, T interval, go to Data. So make sure you're in Data. There's list 1, 1.95. And then calculate, and voila, there's your confidence interval. It's pretty simple. Now, if I had done this by hand, this is what I would have gotten based on the one var stats I had earlier. And that's the interval I have here, calculating by hand, which is very similar to what we got on the calculator.